Hello everyone. I am Harsh Gupta, student of VIT Chennai, studying CSE. I'm a third year student. So this video is regarding the project that I'm about to do in NLP, which stands for Natural Language Processing, and what model will I be using to do so. So as you can see, the title suggests my project will be a next word prediction model, which will be based on the topic of LSTM, meaning long-term short memory. LSTM now is an invaluable asset to the field of AI and ML, which is very often used in NLP as well, since NLP is a combination of, we can say, AI and other uh, child fields. So we will be learning more about this in this video. Yes. So now here we see what is LSTM. So let us understand, before understanding LSTM, it is important that we understand what exactly is RRN, which stands for recurrent neural networks. I'll explain this to you using an example. So let's say humans don't start their thinking from scratch every second. Even as we read this presentation, we understand each word based on our understanding of previous words that we've learned, which are English alphabets and some words which we learned in our first and second classes. We don't throw everything away and start thinking from scratch again. So every time we read something or we hear something, we always recollect the word which we learned in our childhood, and we understand the meaning of it. That's how our thoughts have persistence. So traditional neural networks can't do this, and it seems like it's a major shortcoming. For example, imagine you want to classify what kind of event is happening at every point in a movie. It's unclear how a traditional neural network could use its reasoning about previous events in a film to inform later ones. Thus, recurrent neural networks address this issue. They are networks with loops in them, allowing information to persist. Now, to understand what exactly is LSTM, LSTM stands for long term short memory networks used in the field of deep learning. It is by nat- its origin is from deep learning. However, it is used in NLP very often. Even our project that we are doing is heavily based on LSTM and other short and other small NLP topics such as tokenization and embedding. So coming back to LSTM, it is LSTM has a feedback connection that is capable of processing the entire sequence of data apart from single data points such as images. This finds applications in speech recognition, machine translation, etc. LSTM is a special kind of RNN which shows outstanding performance on a large variety of problems. Now, in short, if we were to summarize what exactly I said for LSTM, long LSTM units or blocks are part of a recurrent neural network structure which are made to utilize certain types of artificial memory processors that can help these artificial intelligent programs to more effectively imitate human thought. Now, uh, going to the next slide, we have structure of LSTM. Now, this we I need you all to look at this figure that is shown in here with a little importance, because this is how exactly an LSTM structure looks. The LSTM is made up of four neural networks and numerous memory blocks known as cells in a chain structure. A conventional LSTM unit consists of a cell, an input gate, an output gate, and a forget gate. The flow of information into and out of the cell is controlled by three gates, which, as I said, are input, output, and forget gate. And the cell remembers values over arbitrary time intervals. The LSTM algorithm is very well adapted to categorize, analyze, and predict time series of uncertain duration. Okay, moving on to the next slide, we have forget gate. Now, as I told you, the three gates let us go back and see again. The three gates control the flow of information in and out of the cell. So here we have forget gate. Let us understand what exactly is forget gate is. It is the information that is no longer useful in a cell state is removed with the forget gate. It's pretty standard and exactly what it stands for. There we have two inputs, xt and ht minus 1, which is for the previous cell output, and the resultant is passed through an activation function which gives a binary output. If for a particular cell state the output is 0, the piece of information is forgotten, and for output 1 the information is retained for further use. Here we can see we have uh, given a formula which proves the same as told. Moving on to the next slide, input gate. Now this is the second gate which we have, and it stands for the addition of useful information to the cell state is done by input gate. First, the information is regulated using the sigmoid function and filter the values to be remembered similar to the forget gate using inputs ht-1 and xt same. Then a vector is created using tan h function that gives an output from -1 to +1. Let us note here the range for the output in the previous was as a binary output 0 or 1. However, we have a range here for the input gate from -1 to +1, which contains all the possible values from ht-1 and xt. At last, the values of the vector and the regulated values are multiplied to obtain the useful information. As they are multiplied, it is shown in the form two formulae given here. Moving on, we have the output gate. The task of extracting useful information from the current cell state to be presented as output is done by the output gate. Pretty standard as its name. Here we have the given diagram of the output gate. As we can see, we have the tan h function and we have the sigmoid function. The information is regulated using the sigmoid function and filtered by the values to be remembered using inputs ht-1 and xt. At last, the values of the vector and the regulated values are multiplied to be sent as an output and input to the next cell. So here we have the two formulae for the sigmoid function and the ht for gate, ht input. Now, what exactly is the logic behind LSTM? We will understand this using the given diagram here. So the core idea behind LSTMs is that the key to LSTM is the cell state, the horizontal line running through the top of the diagram. The cell state is kind of like a conveyor belt. It runs straight down the entire chain with only some minor linear interactions. It's very easy for information to just flow along it unchanged. The LSTM does have the ability to remove or add information to the cell state, carefully regulated by structures called gates. Now, gates are a way to optionally let information through. They are composed out of sigmoid neural net layer and a pointwise multiplication operation. Here we see information can be added or removed from the cell gate in LSTM and is regulated by gates, as I told before. Now, the sigmoid layer outputs numbers between 0 and 1, describing how much of each component should be let through. A value of 0 means let nothing through, while a value of 1 means let everything through. Now, if we were to understand the step by step LSTM walkthrough, we again go to the diagram, and I want all of you to please understand what I'm trying to say and please continue to look at the diagram very importantly. Now, understanding step by step how the LSTM works. The first step in our LSTM is to decide what information we're going to throw away from the cell state. This decision is made by a sigmoid layer called the forget gate layer. It looks at ht-1 and xt and outputs a number between 0 and 1 for each number in the cell state ct-1. A 1 represents completely keep this while 0 represents completely get rid of this. Let's go back to our example of language model trying to predict the next word based on all the previous ones. In such a problem, the cell state might include the gender of the present subject so that the correct pronouns can be used. When we see a new subject, we want to forget the gender of the old subject. Now, the next step is to decide what information is going, what information what new information we're going to store in all the cell state. This has two parts. First, a sigmoid layer called the input gate layer decides which values will update. Next, a tan-H layer creates a vector of new candidate values (CT) that could be added to the state. In the next step, we will combine these two to create an update to the state. Now, in the example of our language model, we'd want to add the gender of the new subject to the cell state to replace the old one we're forgetting. It's now time to update the old cell state CT-1 into the new cell state CT. The previous steps already decide what to do. We just need to actually do it. We multiply the old state by ft, forgetting the things we decided to forget earlier. Then we add it into ct. This is the new candidate values scaled by how much we decided to update each state. Sorry for the inconvenience. Now continuing, and let's not derail by a path. This is the new candidate value scaled by how much we decided to update each state value. In the case of language model, this is where we'd actually drop the information about the old subject's gender and add the new information, as we decided in the previous steps. Now, keep looking at the diagram to understand what exactly am I talking about when I refer to FT, IT, CT, CT-1, etc. Finally, we need to decide what we're going to output. The output will be based on our cell state, but will be a filtered version. First, we run a sigmoid layer which decides what parts of the cell state we're going to output. Then, we put the cell state through tan-H to push the values to be between -1 and 1 and multiply it by the output of the sigmoid gate so that we only output the parts we decided to. For the language model example, since it just saw a subject, it might want to output information relevant to a verb. In case that's what is coming next. For example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into if that's what follows next. Moving on forward, we see tokenization. Now, tokenization is a very crucial and important subfield of computer science, AI, and NLP. NLP is we can say is natural language processing is a combination and a subfield of major computer science fields like AI, deep learning, IoT, etc. And tokenization is a very, very important part of NLP. In order to understand what exactly tokenization is, let us understand let us read what is given in the presentation. Now, it is difficult to perform as the process of reading and understanding languages is far complex than it seems at first glance. Let, if I were to give you an example, let us say you are teaching a room full of 30 children of the age of 5 to 6 years old. If you want them to learn a new word like a cat or a dog, you just don't say the word out loud. You divide the word into its alphabets like CAT, and then you pronounce the word cat. Similarly for dog. It goes not just for kids but even for adults and people who struggle with pronouncing long English words or any language words. The key idea is to break up the words into small pieces of word and then pronounce them or understand what exactly the small pieces of the word mean so that we can understand what the longer word is. That is what exactly is tokenization. Tokenization is the first step in any NLP pipeline. It has an important effect on the rest of your pipeline. A tokenizer breaks unstructured data and natural language text into chunks of information that can be considered as discrete elements. The token occurrences in a document can be used directly as a vector representing that document. This immediately turns an unstructured string or a text document into a numerical data structure suitable for machine learning. They can also be used directly by a computer to trigger useful actions and responses, or they might be used in a machine learning pipeline as features that trigger more complex decisions or behavior. As we can see, tokenization in simpler words can separate sentences, words, characters, or subwords. When we split the text into sentences, we call it sentence tokenization. For words, We call it word tokenization. As seen in the example, we have a sentence: life is a matter of choices, and makes every choice you make makes you. So this one is a complete sentence. So if we were to apply a sentence tokenization, one token would form the whole complete sentence. Now, for word tokenization, let's say the sole meaning of life is to serve humanity. When we apply word tokenization, each word of the sentence is broken down and converted into one token itself. So here we have the tokens: the sole meaning of life is to serve humanity. Each word is a token in itself. That is what exactly is tokenization, which is a very, very crucial aspect and important part of our project, and as well as in NLP. Moving on, we have now the question arises: why LSTM? Why not any other approach? Why not any engram approach? Why not any traditional neural network approach? Why LSTM? Now, to answer this, let us understand how exactly is LSTM different from any other traditional neural network. LSTM was designed by Hochreiter and Schmidhuber. I'm sorry if I pronounced their names wrong. It tackled the problem of long-term dependencies of RNN, in which the RNN cannot predict the words stored in the long-term memory, but can give more accurate predictions from the recent information. As the gap length increases, RNN does not give an efficient performance. LSTM can by default retain the information for a long period of time. It is used for processing, predicting, and classifying on the basis of time series data. So we saw that how LSTM works, and how an RNN works. So traditional now, if as continuing, traditional neural networks suffered from short-term memory. Also, a big drawback is the vanishing gradient problem. While back propagation, the gradient becomes so small that it tends to zero, and such a neuron is of no use in further processing. LSTMs efficiently improve performance by memorizing the relevant information that is important and find the pattern. Now, if I were to break all this down into very simple words, let us understand why LSTM using an example. Let's say, when I say a sentence something like the sky is dash. So by default, the traditional neural network will fill the blank with the word blue, because as we all know, the sky is blue. However, if we were given some context very early in the text document that we are using, something like it is raining heavily today, and then after a while we again come to the sentence the sky is dash, what should be the output, uh, which is to be filled in dash? If we were to use some traditional neural network, it will again fill the sky is blue. However, it does not read the context which was earlier stated in the text document, that it is raining heavily today. That means we have black clouds over our heads. Hence, if we use with the use of LSTM, it uses the context given in the document or in the text dictionary that we are using. It reads the context and then fills the blank accordingly. Hence, when we are if we use LSTM model, the answer should be the sky is black, because we have black clouds over our head. It's not blue because it's raining heavily and we don't have rain and clear sky. That is the context given, and that is why LSTM has an upper hand over traditional neural networks or traditional RNNs. That is why LSTM is such an important and crucial part of NLP and for our project. So this idea of LSTM is very useful when we have its applications, which we are going to see forward. When we let's say when we are chatting to someone and we are using some default or general English sentences, it is very important to understand the context by that we are talking to the other person by the AI, so that the AI can recommend words to us while chatting. So which are correct according to our context. Moving on, now we come to the applications of LSTM. LSTM is such a vast topic and such a volatile subject that it has handful and many applications. Some of them are stated, such as language modeling, machine translation, handwriting recognition, image captioning, image generation using attention models, question answering, video to text conversion, captions, polymorphic music modeling, speech synthesis, speech to text conversion, and proteins secondary structure prediction. These are all applications of LSTM, and most of them are natural language processing related applications. Similarly, the application that we are using of LSTM is one particular application for which we are using LSTM is next word prediction model. In this model of our NLP project, we shall be using LSTM approach to predict the next possible word of a given text dictionary, allowing us to predict the text with the help of the preceding text available. As I said, the preceding text helps us to give helps us to give the context of the conversation or the the text that we're actually talking about. This application is majorly used in autocomplete or suggested responses while chatting in WhatsApp, Facebook, Instagram, etc. As I mentioned before, while chatting, you may have seen when you are using your keyboard on your phone or your laptop, you have while chatting you see some suggested words available. Even when you are googling some stuff, you see suggested words available. All these suggestions are based on our previous um, searches or previous chats that we do or we have done to understand the context of what exactly we are talking about. And this model is done this LSTM model is a very correct and important feature to do so. Now, let us understand how exactly we are using LSTM in our project. So, here we have the mind map, or you can say the graph, or uh, a table kind of structure which we have, such as embedding input layer, embedding LSTM, LSTM layer 2, dense, and dense 1. So let us understand by this graph, by the text that we've written here. LSTM model uses deep learning with a network of artificial cells that manage memory, making them better suited for text prediction than traditional neural networks and other models. In building our model, first an embedding layer, two stacked LSTM layers with 50 units each are used. Keras, which is a package in Python which we'll be using while doing our code, we will be including that package, offers an embedding layer that can be used for neural networks on text data. The embedding layer is initiated with random weights and learns embeddings for all the words in the training dataset. It requires the input data in an integer encoded form. This data preparation step can be performed with the help of a tokenizer API also provided by Keras. As I said before, we are using tokenization, a very important subfield of NLP and a topic of NLP, which we are implementing it with LSTM. So here we will be using a tokenizer AI API, which also is included in the package of Keras, which will be installing for our code. The two LSTM layers are followed by two fully connected or dense layers. The first layer has 50 units, and the second dense layer is our output layer and has the number of units equal to the vocabulary size. As for each input, the model will predict the next word from our vocabulary based on the probability. Categorical cross entropy is used as a loss function. Hence, basically, what our input and output will be, our input will be a text document or a text dictionary, which we'll be using as reference. Then, and in our output, we will be writing an incomplete sentence or some two consecutive words to guess or predict what the third word should be according to the reference document given. And use it, and the model used will be LSTM and tokens. In conclusion, Uh, I'd like to just say that earlier I mentioned the remarkable results people are achieving with RNNs. Essentially, all of these are achieved using LSTMs. They really work a lot better for most tasks. Now, if we write LSTMs as a set of equations, it looks pretty intimidating. Yes. However, I am hope I am hoping that walking through them step by step in this presentation and this video has made them a bit more approachable. So, in ending, I would just like to say that have a bright LSTMs are the way of the future in AI and NLP related projects and work in NLP related work. So, and I would like to thank my teachers and my friends for understanding what exactly this project is understand for helping me understand about NLP and the future of NLP in our world. And I would like to end this video. My name is Harsh Gupta, 20BC1310, and thank you.